Now let's talk a bit about exponential functions. These are functions which do involve exponents, so all of the exponent rules you've ever learned do still hold true. These are very important with cases like compound interest. The spread of disease is exponential growth, and even human population is an exponential growth situation. Now, what really is an exponential function? An exponential function will have a base, and it will be raised to an exponent we'll call x, and that will equal our output. So many times the function may be written as f of x equals 3 to the exponent x, where x would be your input value or your domain element. Since that domain is an exponent, the domain is always negative to positive infinity. Now here's an example to do with your calculator. Most scientific calculators, well, all of them, will have an exponent key. Today I'm going to be using the TI-30X to demonstrate. I can type in the 6 and then the exponent key, which looks like this on my calculator, and then I would simply type the key that will tell the computer, the calculator, I want a negative number, the negative sign, and then I type in 1.9, and then the equals key on this calculator has enter. When you do this, you will get a decimal answer. You will normally be asked to round off. Let's say I want to round to the nearest hundredth. Remember the place values that you've learned in previous math classes. The hundredths place is the second place behind the decimal. So if I see this long decimal on my calculator screen, I go to the second place, and for just a moment I glance at the third place. If that's 5 or larger, I round up. But since it's below 5, I can drop those digits and just say my answer is 0.03. A second example is using the value of e. Now, e is a number called Euler's number. Mathematician Euler discovered that this is the number of constant and continuous change. Most calculators, you have to use a shift key to access Euler's number unless you have a graphing calculator. Many of them will have Euler's number programmed directly onto a key. Since I am using the TI-30X, I must type this in using the following steps. The shift key is the blue second key in the upper right corner, and then I will click the key that says LN, stands for natural log, which is the corresponding function, the inverse function to Euler's number, and it will automatically put the exponent symbol. I then just have to type in 1.2 and then the enter equals. Again, I will get a long decimal answer. In this case, it's 3.3201169. And if I'm looking at the nearest hundredth, I look at the second place, glance to the third. Since that is less than 5, I drop those digits. So this answer would be 3.32. Now here's an example with graphing. You're given an exponential function with a base of 1/2. One by one, we must take these values and substitute them in. Feel free to use a calculator for this. 1/2 to the -2 will actually, if you're working it by hand, it will invert that and square that, which would give you 4. Again, you could use the calculator. Then I have 1/2 to the exponent -1, which simply inverts that, which leaves me with 2. Then I have 1/2 to the exponent 0, and if you remember the 0 exponent rule, that always changes the base to 1. If I have 1/2 to the power of 1, then that is the same thing as the base 1/2. And lastly, I have 1/2 squared, 1/2 times 1/2 is 1 over 4. So that's 1 over 4 or 0.25. Notice that the directions say to use fractions or integers. So if you get values like 0.25, convert those to the fraction 1/4. Then to graph these, you would choose your graphing tool online and you would have -2, +4, -1, and +2, 0 and 1. 1 would be 1/2, you can estimate that, and 2 would be at 1/4. So this creates a curve that is decreasing to the right and increasing to the left. If I look at the multiple choices that are given below to choose my correct answer now, I would see that my correct answer would be choice B. Now, the last very practical application of exponents would be compound interest. You are given a regular compound interest formula and a continuous compound interest formula. The only time you use this one that looks like the word PERT is when you have continuous compounding specified. Here's how to use the formula. We want to find the accumulated value of an investment of $25,000. So the principal, we say, which is the P, is equal to $25,000. We are going to leave that for 6 years. The time, which is the T, is 6 years. We will have that in an interest rate of 4%. The rate, which is the letter R, is 4%, but we must change that to a decimal, 0.04. Move the decimal 2 places to the left. Now, part A says to compound this semi-annually. The word semi-annually means twice a year. The letter N in the formula stands for the number of compounding periods. That means how many times a year is the money going to be compounded. Semi-annually means twice. So N here would be 2. Now we set up the formula. A equals 25,000 times 1 plus the rate 0.04 divided by the compoundings 2 raised to the exponent of 2 times 6. Now I normally put this either in parentheses or I go ahead and just call that 12. Now you will type this into your calculator to get the final accumulated amount. After typing it in the calculator, you'll see that the accumulated amount is $31,706.04. So this would be the answer to part A. Now part B is very similar, except it is compounded quarterly. Quarterly means 4 times each year. So when you set up the formula, the only thing that changes would be the number of compounding periods. So instead of 0.04 divided by 2, it's divided by 4. And instead of 2 times 6, this would be 4 times 6, which would be quarterly times the year. You can pause this video and type it into your calculator to see what you get for the accumulated amount. You should have gotten that the accumulated amount is now $31,743.37. Notice that this is slightly higher than the answer in part A because your money is compounded quarterly, which is twice as many times as semi-annual. Now, part C. Part C says to work this compounded monthly. Well, there are 12 months in a year. So when using this formula, again, the only thing that changes in the formula is the number of compounding periods, which would now be 12. And that would be 12 times 6 years is my exponent. Go ahead and pause the video once again to see what you get. Now here you should have gotten the accumulated value was $31,768 and 55 cents. Again, slightly more than when you had a compounding of quarterly. Last but not least, Part D asks you to compound this money continuously. In theory, that would be wonderful. In practicality, that's very rarely done. And so we have A equals PERT, the principal, which is 25,000, Euler's number, which we discussed just a moment ago, and then the exponent is the rate, 0.04, times the time, which is 6 years. Notice there are no compounding periods because continuously means, in theory, your money is constantly being compounded. Now, type this into your calculator and see what you get. As expected, I hope, you should get a slightly larger number, which is $31,781.23. Because technically, compounding something continuously is even more than monthly. I hope this gives you an idea of how to really use, in a practical way, the exponential functions.